started. Okay, so I'm going over graphing logarithmic functions today, and technically you don't have any homework on the graphing portion of it until week 8, but it is part of the reading this week, which is why I'm covering it. Plus, that way when you get to it, when you get to the homework, you'll be like, oh, I know what to do. So it's not as bad as it seems. I know a lot of people struggle with graphing, and of course that's like what half of the class is that we do. So I'm going to just start with what a logarithmic function is. And so we have some number, real number b. B has to be positive, and it's not equal to 1. And then our variable x has to also be positive. So we can't plug in negative numbers for x. They have to be positive. But a logarithmic function is written in this form. So we often abbreviate logarithmic as log. And this is read as log base b of x. The way to think about a logarithmic function is that it is actually the inverse of an exponential function. So you're familiar with exponential functions, and the log inverses or kind of undoes it. So you can convert between the two with this relationship. So the base of a log is the same as a base in an exponential function. Oh, I see, I actually forgot to finish my, this should say y equals, so that you have a y there on the left. What you take the log of, basically you take the log of some number, and then it's giving you the exponent. So when we say that it's something like the logarithmic undoes an exponential, is it basically tells you what the exponent is on something. So it's the inverse because it undoes an exponent. And so when we solve these things, which you will do later, you'll learn how to solve these types of equations. You solve an exponential where your variable's in the exponent by taking the log, because it basically removes the variable from the exponent and then puts it somewhere where you can work with it. And we can't take logs of negative numbers because no exponential, essentially the exponential functions don't give you negatives out. If you try to do like a log of -2 in your calculator or something like that, you're going to get an error. So mine, when I plug it in, says domain error. We cannot have negatives inside that we take a log of. You're going to get an error. So I'm focusing on graphing these things today. And so just like with exponential functions where you have exponential growth and decay, you also have logarithmic growth and decay. And they look different than the exponential. It's like they look like sideways exponentials, actually. If you rotated it, you can get like sort of a sideways exponential. And that's because of the fact that they are inverses. So it's like a reflection and a rotation to get to a logarithmic graph. So if your base on your log is greater than 1, we get what is known as logarithmic growth. And so that looks like the picture on the left. And notice that our graph never goes into the negative side of x because we can't plug in negative numbers for x. And then if your base is between 0 and 1, because we can't have a negative base, then it's the graph on the right. Again, we don't have any negative x values. We're only on the positive side of x, and then it's like going down. These are sketches. These are not perfect graphs, but these give you the general shape of what a logarithmic graph looks like. So just comparing between the growth and decay of a logarithmic function, your domain is always 0 to infinity unless you have some transformations. And then the range is -infinity to +infinity. Now, if you compare this to exponentials, so inverse functions are basically, if two functions are inverses, their x's and y's get reversed. So for exponential functions, the domain is all real numbers and the range is 0 to infinity. So they're flip-flopped here for a logarithmic because we're flip-flopping the x and y, because it's an inverse. Exponential functions have horizontal asymptotes. If you switch your x and y because it's an inverse, that means the logarithmic functions have vertical asymptotes. And then the rest is basically the same. If it's a growth function, it's increasing. If it's a decay function, it's decreasing. But the key difference between the exponential and the logarithmic is that they're very similar. It's just the x and the y are flip-flopped. So if you happen to have notes for like your exponential and then you put it side by side with your notes here for the logarithmic, you'll be able to see how it's just flip-flopping all the x's and y's. And I have a video on the graphing an exponential function, and I formatted this one exactly the same as that one, so that way you can just have them side by side and you can see those similarities and differences. So graphing these. So the first thing we always do whenever we graph is to determine if there's any transformations, whether we're shifting things left or right, or if we're taking, we're reflecting, we're moving things up and down, we need to look for those. And then we need to figure out where the vertical asymptote is for our logarithmic function. And we do that based off of the transformations. Then we have what I say, use the base table and transformations to get new ordered pairs. So I take this existing table, which is for the base function, logarithmic function, like the basic one. If you want to say the family, we talked about, we have parent functions. This would be the parent function for a logarithmic function. I take this table and then I apply the transformations to these 3 points on the table to get a new table. That's the table that I graph. So that's how I graph anything that has transformations. And that's how I graph things here with like a logarithmic function, is I use this base table, plug in my numbers, apply the transformations, and then that gives me new ordered pairs. So that's what we're going to be doing. So transformations, we've talked about this before, where you shift left, right, up, and down, all that. How does that work when you have a logarithmic function? So anything that happens inside, let me change that color. Inside with x shifts left and right. And we always do the opposite. So if it's a minus, that means we shift right. If it's plus, we shift left. So x minus h shifts right. X plus h shifts left. These are the same rules that we have for transformations that we've worked with any time a graph. But like the transformation rules apply the same no matter what the parent function is. Then this plus k going on, that's our vertical shift up and down. So vertical shift up, down, and that basically follows the sign. So plus k is up, minus k is down. And so that just moves your graph up and down. And then the number in front of the log, whatever we're multiplying the log by, that is a scaling factor. So it scales. And so this is usually where you'll see stretch or shrink as the term's used. So if it's, we look at the absolute value basically. So if the number, if you ignore the sign, if the number is greater than 1, then we are stretching. If it's less than 1, we're shrinking. And then a negative is a reflection. So negative it reflects. If you take the absolute value, that's greater than 1, that is a stretch. And then if that absolute value, that is a shrink. And so that just, that applies to the y values. So I'll just write that scales y. And so it's just, you're basically multiplying your y by some value, and then it's either going to get bigger or smaller. So that's what the transformations, basically what they do. And the order of transformations that we usually do is we always do x transformations first and then y. X transformation, you do your shifts left or right. Then when you do your y transformations, you follow the order of operations, which means that your stretching and shrinking happens first because that's multiplying. And then the vertical shift up or down happens next because that's adding or subtracting. So we follow the order of operations when we apply transformations. So I've got 4 different examples of logarithmic functions. We're going to go through, identify the transformations. We're going to go through the whole graphing process. We'll identify what the domain and range is and the equations for the asymptotes. That way you can see how to, well, you'll see how to graph these, but also you'll be analyzing the graph, which is a good skill to be able to read the graph and know what it says. So our function here is f of x equals log base 3 of x plus 2. So first thing is, I'm going to just, before we even do any transformations or anything like that, I'm going to fill in my table, the base table for a log base 3 graph. So the way that, when I fill in the table, our table always has y values of -1, 0, and 1, and then we have to figure out what are the x values that go with that. So I'm going to go back to my table here. So for a y value of -1, x is 1 over b. And then for a value of 1, x is b. And then we always have the ordered pair 1, 0 every time. So that's really nice. So I know I'm going to have 1, 0. For -1, it's 1 over b. Now b in this case is 3. Our base is 3. That's the number, that's the subscript there. So we're going to have 1/3. And then b, 1. So that's going to be 3, 1. So I'm just taking that table that I had written and I'm plugging in what b is. So that gives me what the basic table is that I'm going to be working off of. This is not what we're going to graph because we haven't done any transformations to it yet. So when I look at my graph, or my equation, sorry, f of x equals log base 3 of x plus 2. So we have one transformation here, which is from the x plus 2. And so if it's a plus, we are going left. So we are shifting left by 2 units. And so what that means as far as x is that we're taking our x values and then we're basically subtracting 2 from them. So I'm going to take my table here and I'm going to make a new table. And I'm basically going to be subtracting 2 from each of my existing x values. And this will be how I do my shift. The y values we're not changing because we don't have any transformations on y. The only transformation we have is dealing with the x. And so I need to subtract 2 from each of my x values. Now I'm going to just use my calculator, especially with the fractions. My calculator does fractions, so this is -1 and 2/3. And I'm going to leave it as a mixed number because it's a lot easier to graph. 1 minus 2 is -1. 3 minus 2 is 1. So I've just applied our transformation to our table, and this is what we're going to be graphing. These are the ordered pairs that we're going to graph because we now just moved everything left 2. So I'm going to have to estimate on my graph -1, 2, and 2/3. And then the y value is -1. So I'm just going to kind of eyeball where that is. Then I have -1, 0. And then I have 3 minus 2, which is 1. So I have 1, 1. So I know that I'm going to be connecting those 3 points together, but I need to know where my vertical asymptote is. So for our base graph, our vertical asymptote is x equals 0. So since our transformation is occurring to x, our transformation also occurs for the vertical asymptote. So we subtracted 2 from all of our x values, so we're subtracting 2 from the vertical asymptote as well. So our vertical asymptote is going to be x equals -2, because we need to shift it over to the left. So I'm going to just kind of draw that in as best as I can with a vertical dashed line. And so that helps me know that my graph, when I connect this, I can't go beyond that line. And so then I can finish my graph. I connect those 3 points, and then I have my drawing. So I've identified the transformations, I've graphed, and I actually, in order to get my graph, I had to give the equation for the asymptote. So the last thing that we need to do is identify the domain and the range. So our domain, so if we can go back to our table here, we have something that's growing because it's getting bigger as it goes to the right. Our domain is usually 0 to infinity. Now our transformations moved all of our x stuff left, and domain is x. So that means our domain also moved to the left by 2 units. So our domain is -2 to infinity. And it's a parenthesis at -2 because we have a vertical asymptote at -2. So we can't actually reach that point. So any transformations that occur, even if anything that we did to x that was a transformation, occurs to your vertical asymptote and the domain, because those are also x-based. And then our range for a logarithmic function is -infinity to +infinity. And it's still going to be that range. We didn't make any changes to y. So our range is -infinity to +infinity. And you can visually see this on the graph. So on the graph, we can see our domain. We don't have any numbers smaller than -2 on our graph. And then we are going forever to the right. And then our range, because we have an arrow down at the bottom, and then we're increasing to the right, that's going to go on forever in both directions. So our range is all real numbers here. Are there any questions? Okay. Here's a new example. All of these I'm doing log base 3, so that way we can reuse our table. We don't have to make a new table each time. So we have a function f of x equals 2 plus log base 3 of x. So for log base 3 of x, we're going to use that same table. It's 1/3, 1, and 3. So it's the same table that we used on the previous, because it's still log base 3 of x as our parent function. And then we're going to be doing transformations based off of that. And so I can even write, so our vertical asymptote for the base function is x equals 0. We may have transformations in that, we may not. So let's look at the function that we have. So we have 2 plus log base 3 of x. So first thing is you look to see if there's anything that has occurred to x. Did we add or subtract anything to x? And we didn't. We just have log base 3 of x. So there's no transformations applied to x. We're not shifting left or right. Next is there a number multiplied in front of the x or in front of the log? And the answer is no, because we don't have a number in front of there. We have a plus in between these. It's not multiplied, so we're not doing any stretches or shrinks. So then the last thing is vertical shifts up and down. And normally we put them at the end of the function, but it's also correct if you put them at the front. So we have 2 plus log base 3 of x. This is the same as if we wrote log base 3 of x plus 2. So let me fix that 3. So that plus 2, this is a vertical shift up and down because we're adding 2 to a y value. So we have a vertical shift. And because it's a plus 2, we're moving up. So we're moving up 2 units. And this is equivalent to taking our y values and we're adding 2 to the y values. So that's our transformation. That's the only transformation we have. So that means when I'm making my table, I need to add 2 to all of these y values in order to get my transformed table so I can get what I'm actually going to graph. So if we were to actually graph 2 plus log base 3 of x, there's been no transformations to my x values, so those are all the same. And I'm adding 2 to all the y values. So -1 plus 2 is 1, 0 plus 2 is 2, 1 plus 2 is 3. So I'm going to graph those points. I'm going to kind of eyeball it here. And then we need to think about, okay, whoops, I did -1/3. Oh, help if I actually graph my correct points. And then we need to look at, okay, our asymptote. So our vertical asymptote is x equals 0. And because we did not do any transformations on x, it's still x equals 0. So our vertical asymptote is still going to be basically the y-axis here. So when I connect these, I'm going to get very close to the y-axis, but never actually touch it. So you can see that basically we have this shape, and the shape has moved up. If we kind of compare it here our shape moves to the left. We have the same shape, but we're moving it up because we shifted up by 2 units. So our domain, because our domain involves x, the domain is unchanged from the parent function. So it's still 0 to infinity. And we did change our y. We shifted it up by 2 units, but if you add 2 units to infinity, you're still at infinity. So our range is still all real numbers, -infinity to +infinity. Now notice if you were asked about like the intercepts, we have no y-intercept because our graph never crosses the y-axis, but we do have an x-intercept. And to solve for that, you would have to solve by taking exponentials, and that's covered in another video, basically. You'll learn that later. Are there any questions? Okay. Here our function is log base 3 of x minus 1 and then -3. So we have 2 transformations going on here. I'm going to first just write down my parent function, get that table that we're going to be using. And we're going to look at our transformation. So we have a transformation occurring to x because we have this x minus 1. So we do the opposite. So we're adding 1. So that means we're shifting it to the right. Shift right 1 unit, which means we're taking our x values and we're adding 1 to them. So I'm going to just kind of mark that in on my table here. Now we also have a transformation here with a -3. This is a vertical shift, and it's going to be down because it's subtraction. So we are shifting down by 3, or we're basically taking our y values and we're subtracting 3. So I'm going to write that down here. So we have 2 transformations going on. We have a transformation to x, and then we have a transformation to y. Now the change in the x is also going to affect our vertical asymptote. So our vertical asymptote is usually x equals 0, but because we're shifting right by 1 unit, so we're also adding 1 to the vertical asymptote. And so we're actually going to get x equals 1 as our vertical asymptote because we're adding 1 to it. So I'm going to just draw that in right now. So I'm going to fill in my table. I'm going to make a new table here based off of our transformations. So I need to add 1 to each x value, and I'm going to just use my calculator to put it in fraction form. I have 1 1/3, 2 and 4. And then the y values we're subtracting 3, so that gives me -4, -3, and -2. So I'm going to graph these values. Approximately 1 1/3 is at -4, so I'm just eyeballing that. 2, -3, and 4, -2. And so I'm going to then very carefully connect my dots. And so that's how we get our graph. And so you can see our graph has now moved to the right and it's moved down. So like if you compare it to this one where we moved it up, you can see it's moved down. Here we moved it to the left. Now we've moved to the right. We have multiple transformations going on. So we found our equation for the asymptote. That's at x equals 1. So all that's left is domain and range. So the domain is normally x, and that's usually 0 to infinity. So I can put this in yellow. 0 to infinity. But when we do transformation to x, it also affects the domain. So we're also adding 1 to basically the domain values. So our new domain is now 1 to infinity, because adding 1 to infinity is still infinity. And then our range is still all real numbers because we've got infinity in either direction. So subtracting 3 from either of those values is really not going to change anything. Any questions? Okay, this is my last graph here. We have f of x equals negative log base 3 of x. So again, we're looking at log base 3. So I'm going to just fill in my table. We don't have any transformations to x because we're not adding or subtracting the x. We do have a multiplication going here, and it's a negative. So the negative is a reflection. And if we put a number there, that would be -1. So this just means that we're multiplying the y values by -1. So that's what that's telling us, is that we're going to be multiplying all of the y values by -1. So I'm going to just write that. I should actually just put these all in parentheses here. So we're multiplying all of our y values by -1 to do a reflection. And then we don't have anything added on or subtracted, so that's the only transformation that we have. So we haven't changed our vertical asymptote because we didn't do anything to the x. So that's still going to be x equals 0. So I'm going to just kind of eyeball really badly my dashed line there, just so we have that. And now I'm going to make my new table based off of those transformations. Our x values are unchanged. And then I'm multiplying all my y values by -1. So -1 times -1 is 1. 0 times -1 is 0. 1 times -1 is -1. And so now I'm going to kind of eyeball and plot those numbers. And you can see that what the reflection did is it basically turned our graph upside down. Oh, I missed. There we go. It's a little better. So it takes what we had and it turns it upside down, and it takes something that would normally be a growth and it now is making it decay. So it's just flipped everything upside down. Because we didn't do any transformations to x, our domain is the same, so it's still 0 to infinity. And then our range is still -infinity to +infinity, because multiplying by y by -1, it doesn't actually do anything. The range will still be -infinity to +infinity. So that is what this graph looks like as a transformation. Any questions? Okay. So one thing to know about logarithmic functions is that we do have another type that's called the natural logarithm. So when you learn about exponentials, you learn about Euler's number, E, which is a special number. And when that number is the base of your logarithm, we call it the natural logarithm. And we actually have a new symbol for that. So it is abbreviated LN. So that's the letter L, the letter N, and that just comes from the French, which I think is just literally logarithm natural. So that's why it's LN versus NL. But it's a new symbol. So when you see LN, that just means your base is E. And one thing to note is that a lot of computer systems that do mathematics, if they have a function called log, it's usually the natural log and not a base 10 log. And this is in the more advanced kind of computer systems or anything. Like on my TI 30X calculator, I have a button for both of those. On my graphing calculator, I have a button just for natural log. There are some math computer programs that you can use, Mathematica, MATLAB. Those, if you type the word log, they assume it's actually the natural log. So you have to actually pay attention to that and know what it's doing, because it does make a difference in what you're graphing or what your answers are, because it has a different base. So just a FYI for anybody who might be going into programming or using those kind of systems, that they do need to be aware of that if they're doing anything with math. So I want to end this with just kind of showing you in Desmos how to graph this, because you may be wondering, well, how do I get the log in Desmos? So I'm just going to open up the graphing calculator. All right, so I usually just type my stuff. So if I wanted to graph y equals log base 3 of x, I type in the word log, and then I hit an underscore button. So it's the button it's like where your minus button is. Shift that, you get underscore, and it puts you below. And then I can hit 3. I hit my arrow to the right to get out of there, and then I hit X, and then that's how I can graph my logarithm. If you're not familiar with like your computer keyboard and those kind of shortcuts, if you hit the button here to get to the keypad and then go to functions, where is it? It might be under miscellaneous. I know it's somewhere here. Okay, here we go. Yeah, if you hit mis for miscellaneous, you have this button that says log A. So let me get a new line. Y equals, I'll go to functions, I hit this log A button, and then it puts me down there. So if I want to have another base like 5, and then what would be in parentheses, like x minus 2, and then I would close my parentheses, and then let's say I needed to add 4 to it or something like that. So the log function, if you're graphing in Desmos, does exist. You just have to go to misc here. This log without the A assumes base 10. And then you can see there's also natural log here as well. So all of those are present in here for you to use if you want to also double check your graphing in Desmos to make sure you have things correct. So it's not too bad. You know, you can verify in Desmos anything that we've done today if you want to experiment and see if we get the same numbers. Are there any questions? Okay, well, that